Thank you everybody for joining us today to our Amy's virtual AI meetup. I'm really excited to be here, and I'll be introducing our two speakers very shortly here in a minute. But before that, I just wanted to take a minute to introduce myself as well. My name is David Chan. I'm the product lead with Amy's industry team, and our team works a lot with companies who are thinking about adopting AI and ML, and we help them understand what AI and ML is and build capacity in that area and figure out what a roadmap of opportunities can look like going forward. Really the goal being that we help them build their skills internally when it comes to AI and ML, and really set them off on the right path to adopting AI and ML and work with them as they're working towards implementing their first projects. Before we get started, I just want to cover a couple of housekeeping items. Ideally, if everybody feels comfortable, or for those who do feel comfortable, please turn your cameras on. It's just great to see everybody's faces when our speakers are presenting. We are recording the session, so wanted to make a note of that. It'll be on our website as soon as we're able to put it up, and also on YouTube for everybody to check out. And if you haven't yet, take a look at the other AI meetups that have taken place in the past, and check those out on our website as well. Kirk and Rohan will be presenting in a couple of minutes here. And so each of them will be presenting separately. Kirk will kick us off, and then Rohan will be presenting. At the end of each of their presentations, we'll have time for some Q&A. So please save your questions until after they're done presenting. And you can submit your questions through the Q&A chat, or just unmute as well and provide your questions at that point. So we have lots of time for questions at the end, I believe. So we should have lots of room for discussion there. I also wanted to mention that our next meetup is scheduled for April 26th. So make sure you follow us on on social media and also through our newsletter to make sure you don't miss any upcoming events. One particularly exciting thing that is coming up is Amy's inaugural AI Week, which is happening May 24th to 27th, which is going to be a really cool celebration of AI in Alberta, celebrating 20 years of investment in AI in the province. So please definitely make sure you check us out on that front. And so let's get started then. I'll stop talking in a minute here. I am really excited for the two speakers that we have presenting here today, Rohan and Kirk. They connect really closely to a program that we are running as part of my team, which is called REMI, and stands for Reducing Emissions Through Machine Intelligence. The goal really being to apply those technologies, AI and ML, for GHG emission reduction, but overall to have a positive impact on our environment. So if you haven't heard about the REMI program or would like to learn more, do look us up, and feel free to reach out to me. And our first speaker, Kirk and Blindman Brewing, actually went through the program last year. And so I'm really excited to hear about where the work is at and where the work is going, which Kirk is going to be talking about in a minute here. So quickly, I'll introduce Kirk. He's the co-founder of Blindman Brewing out of sunny Lacombe. And Kirk, I love your bio, by the way, so I'm just going to read it out, and no changes here. Like their namesake river, Blindman meanders through beer styles and brewing techniques. From kettle sours to heavily dry hopped brews to barrel-aged beers, they create innovative craft beer. He blew the engine on their '79 van, the Dream Machine, on their first delivery run, so now they drive in shiny new vehicles with no souls. Kirk is also an MBA student at the U of A and is currently in France taking an MSc in finance at EDHEC Business School in Nice. And so with that, Kirk, I'll hand it over to you.
Hi, David. Thanks for that. I will share my screen now so that we can all see this presentation. So yeah, like David alluded to, we were a participant in the REMI program with Wyvern, a local space imaging company that's doing great things. Raised a little bit of funds recently. They're doing exciting stuff through imaging to try to capture all sorts of stuff. They got deals with the military. They got deals with some climate change, crop stuff. They got a lot of stuff going on. I'd suggest looking them up if you haven't been aware of them before. So we went through the REMI program as part of a project that's supported by Emissions Reduction Alberta, so agency in Alberta that helps businesses and startups develop technology to reduce our greenhouse gas emissions and meet some of our climate change goals. So we have support from them, and we're working on a project to capture and reuse carbon dioxide that we both produce and use in our brewery. So we have a few key questions that we think AI and ML are really well situated to help us answer. How can we use AI and ML to maximize the quantity of CO2 that we recover? Because that both reduces our emissions, as well as because we are users of CO2, we are currently purchasers of CO2. So we buy bulk CO2 while we produce it on site. So anytime we can maximize the quantity of CO2 we collect and then reuse, obviously there's some huge financial benefits from that. As well as how do we use AI and ML to maximize the quality of CO2 that we recover? Because there's certain, because we're going to be using it in a further downstream process, we need to be of sufficient quality. And how can we use AI and ML to minimize the cost to recover the CO2? Because equipment we use to recover CO2, there's operating costs, there's maintenance costs, etc. And how can we use a question and answer machine to possibly reduce the cost of running that equipment? So there's just some key basic principles. I won't go into like all the details, but basically when you make beer or any alcohol, you have sugars that yeast eats to produce alcohol, ethanol, as well as CO2. Typically, this CO2 is just vented to the atmosphere. It just occurs and it's out the top of the tank. But unlike, say, in a process that also emits CO2, like a classic combustion process, a boiler burning natural gas to produce heat or steam, the flue gas out of a boiler is mainly nitrogen, right? The air we breathe is mainly nitrogen. Nitrogen, oxygen, carbon dioxide, some noble gases. Whereas in a fermentation process, there's no nitrogen. Any oxygen that was in there initially is being consumed by the yeast, because yeast is a living organism. Most living organisms require oxygen to live. So this CO2 is pure, nearly saturated gas. So this is one of those really win-win-win situations where you can have both a producer and a user of CO2 kind of create that circle, really cut down on emissions, cut down on costs. And we use a piece of equipment from a company out of Texas called RLAI Labs. They developed it. They have some, I'm not going to be able to speak to all their ins and outs because I'm kind of covered by a little bit of an NDA, but they use technology that they actually license, I believe, from NASA to do a few things here and there, basically collect CO2 and process it and store it in a way that we can then reuse it. So basically we hook up our tanks, our big fermentation vessels to this equipment. It pulls the gas in, gets rid of any water. It's analyzed to make sure there's no oxygen in it. And then it's scrubbed to remove impurities, and then we can reuse it. And we obviously collect a lot of data from that process. But the data we collect is, I would say, ex post. It's data the data we collect that it happens after the process of yeast turning sugars into CO2. We're collecting data on, okay, what kind of CO2, how much, pressures, temps, all sorts of other variables. But we don't have really good insight into how yeast is turning sugars into CO2. We have a decent amount of information on how yeast is turning sugars into ethanol, because that is what we do. We require good solid fermentation, but we don't really have any information on the CO2, and that's common in literature as well. There's just a little bit of an opaque process. As well as fermentation is optimized for ethanol production. It's not optimized for CO2 production. And so the relation between a solid fermentation that gives you good ethanol content and one that kind of is optimized for CO2, both in quantity and quality, those relations are unclear and really unstudied in the scientific literature, which David can talk about in the REMI program. One of the typical steps in any kind of AI ML process is to consult the literature. If somebody's done something already, copy them, essentially. I'll say that. So in our process, we also have multiple different yeasts. We have every beer we make has a different fermentation profile. It has different amounts of sugars. It has different different proportions of different sugars. You know, the yeast is being required to ferment up to different alcohol levels, and so if the higher alcohol level, the more stressed it is, because it is truly a living organism. It's a biological process, so it's naturally finicky. Yeast dies. You know, you're always hoping that you're getting good, strong yeast. It mutates. There's high mutability, especially when stressors occur. So typically we will reuse generations of yeast until we suspect or observe mutations, and then we'll get kind of what we call a bit of a starter, kind of resets the process. And there's genetic drift. You know, we can say, okay, we know what a strong fermentation profile looks like. We know what a weak fermentation profile looks like, but we don't know about where in the middle. You know, as the process starts to drift, we don't really clear insights into what that process is actually occurring. You know, so we're getting data like this, where you're getting basic ex post data. You know, you're watching to see what the yeast has done, and what the variables that it is changing in your process. You know, so stuff like gravity, so specific gravity, because ethanol and water have different specific gravity. So as you're creating more ethanol, the gravity will change. So we're looking into an AI ML system that we hope will be able to recognize patterns in our biological processes, both faster and more reliably than a human could, as well as we're looking into developing some processes to do a regression to even see, okay, since we can't directly observe this biological process, what are the indicators that are most reliable to feed into a question answer machine? You know, is gravity the one? Is pressure it? Is temperature? Is, you know, the proportion of gas? What are the true indicators that are really telling us what the yeast is doing in relation to the CO2 it's producing? As well as we're trying to understand is how will the question answer machine handle any outliers or process drift? You know, if we pitch with yeast that is, you know, not as vigorous as we hoped and liked, you know, what will it tell us about the CO2 production? You know, because the worst thing we could do is try to capture CO2 and then have contaminated CO2, have to vent all that, or just run a piece of equipment, you know, using up electricity, costing us without any recovery potential, etc. So that's kind of where we're at with our CO2 capture and reuse technology. And now we have a lot of time for questions. If anybody has any information, or sorry, any questions or comments, fire them at me now. I'm willing to chat about pretty much anything.
Fantastic. Thank you, Kirk, for the presentation and the update on where things are at. Definitely have a few minutes here for questions. So if anyone has any questions, feel free to jump in. Maybe Kirk, maybe I'll jump in first and get things started. You know, so you mentioned the equipment, and sort of we went through that planning phase last year. So I guess what's on the horizon, and what's the timeline looking like in terms of when you're thinking you'll be starting to analyze the data and starting to potentially, you know, build out those question answer machines or models that you were referring to there?
Yeah, like everything, the supply chain has been a bit of a headache for everybody. So we've had some delays on the equipment, as well as you know, hopefully a lot of people here in the room are hoping to do things in their businesses, in their careers that are done for the first time. So we will be the first brewery in Canada to use this technology to capture CO2. But I think most people will tell you that is you know, it's great to be the first, but it also is it's a big pain. So right now we're dealing with the regulatory agencies right now to get some of this equipment approved for use in Canada. And it's just been a process. You know, people will tell you in both startup world, etc., that sometimes the first person through the jungle ends up dead on the ground with arrows in their back. So we're going through a lot of that kind of stuff right now. The process is we're still very confident, but there's just been a lot of delays. So we're gathering data right now. We haven't been able to implement the question answer machine yet, but we hope to over this summer, and continue working with Amii in a couple of different fashions.
Great. Thanks. And it looks like we do have someone with their hand up there. Vinod, go ahead.
Hey, Kirk, thanks for the nice explanation of the system which you are trying to implement. So what I'm interested in is, like, is it going to be a self-sustained system, or you will be looking at adding more CO2 into the process? Or, like, will it be the CO2 produced by fermentation will be sustainable for your the process cycle, or you will be adding it? And I have another question as well. I will fire it right away. So you are also looking into MLAI into action to see that, like, what are the, like, you I understand that you capture a lot of data through the process. So what is your key requirements, like what you're trying to achieve from an MLAI implementation? David, you can also chime into that, but is it trying to understand what type of yeast is best suitable for a particular product, or how much sustainable the system is going to be, or will it is going to be like price, recouping the price you are investing? So all those sort of questions.
Yeah, absolutely. So that's one of the, so the first phase of the REMI program that Amii puts on kind of talks about that. They talk about called the business problem first, to really understand, if you have a question that can be answered by AI and ML, and that it's important to understand if it can be even answered, or if that's the right solution. Because, hey, you know, I can't remember the Japanese professor's book off by hand, but you know, he wrote the book Statistical Process Control in the 50s, that, you know, the world used for the next 50 years. You can do things with math first, right? You don't need AI for a lot of processes, but because they're dealing with a biological process, you're dealing with pattern recognition. So our brewers, our brew team are looking at patterns in data, and you can get a good sense of that, but they have there's really no data or no learned experience about CO2. Like, we know pattern recognition in terms of, you know, alcohol production, but really nothing to do with CO2. So, like, to give you a specific, so basically in the REMI program, you know, you're developing multiple ideas about where, because I'm sure you all have the same sense that I do, is that AI and ML can be applied to anything in the whole wide world, and it's probably true. But some of the specifics is like, okay, you know, looking at our biological process, looking at the data, can the question answer machine tell us when we're producing CO2 of sufficient quality and quantity to start running our equipment, for example? So, you know, like Rohan kind of alluded to in the chat, is that can we use it as a controller? Can we, you know, a simple on-off, for example, or, you know, some tuning of the equipment, for example, based on some of the indicators that the process is giving us, and then the AML question answer machine is allowing us to interpret. Because we don't know. Nobody knows. We're gonna be the first ones in Canada. You know, there's a couple of these running in the States, but at this point, everybody is kind of, you know, just learning by doing, which is great. But I think, and we think that AI ML is gonna be better at that than us trying to pick out, you know, I think this might work. And to kind of to your first bit, yes, we definitely hope that this is essentially a self-sustaining process, you know. So spent 60 grand last year purchasing CO2, which is not a huge amount, but it's definitely not a small amount of money. And if we produced all that CO2 we could ever need on site, well, you know, why would we do that? You know, if we can capture it, turn that circle, and most especially, you know, we will probably capture, I don't know, 100 metric tons of CO2 a year, which isn't, you know, so it's a drop in the bucket when we're talking about worldwide greenhouse gas emissions. But if the other, you know, 8,000 breweries on the continent, let alone worldwide, you know, if even half of those can utilize a piece of equipment like this, this, and we all get collectively better about operating it, well, now we're actually making a big impact on greenhouse gas emissions, as well as making, and it's one of those, I believe, rare win-wins in reducing greenhouse gas emissions. Is, wherever you can save money by reducing greenhouse gas emissions, well, that's like, no brainer. So hopefully that answered your question, Vinod.
Yeah, sure. Thanks for doing that.
Yeah, absolutely.
Awesome. And I think you got to Rohan's question in the chat as well. Feel free to, we do have a couple more minutes if anyone else has any questions. I do have another question for you, Kirk. And I think you sort of alluded to it just in the last part of your answer. You mentioned this is pretty still new territory, and it doesn't sound like anybody's doing this right now. So has there been interest from other breweries or other groups that are sort of interested in this? You also talked about, we understand yeast and how it can produce alcohol, but not really, how it can produce CO2. So there's sort of lots of really interesting questions here, and just curious what sort of the community feedback has been.
Yeah. So I kind of said that it's one of those rare win-wins. But us, craft brewers as an industry typically skew towards, doing better, being environmentally cognizant, doing what we can to reduce emissions. So there's been obviously I shouldn't say obviously, but there's been a lot of interest. I get calls all the time. There's probably 24 breweries now behind us in line to get a piece of equipment. Once we convince the authorities that we can, it's suitable, safe, etc., for use in Canada, that will then allow the next 30 in Canada to be commissioned, and that's the goal. So one of the reasons we're partnering with Amii on this project is to get that really the thought leaders in obviously AI nearly the continent, as well as we're partnering with other institutions to really disseminate the information widely, because that really drives the pickup and reduction in greenhouse gases across the board is just dissemination. So what we're doing is we're going to be capturing the data, the performance data on the equipment, financial data on the equipment, and we're going to make that freely available to our friends in breweries. Because I can say, hey, to the brewery down the road from me, I can say, hey, you should buy this, it'll pay for itself, it's not too hard to run, etc. But good hard data really makes the case better than I can say, you should do this. It's like, here, this is the information, it'll pay for itself in 2 years, you'll reduce your greenhouse gas emissions, buy a bunch, make the choice. And I think the choice will be made for them, provided it doesn't fail. One of the other things is that whenever you're dealing with something new is that there's a chance for failure, for sure. And that's the reason that agencies like Emissions Reduction Alberta, granting agencies, which I'm sure most of the people or many of the people on the call, are interact with, is to de-risk things. Is that so you're not making this, for us, it's a $250,000 investment, which is not a small amount of money. And so to have a government partner share that financial burden helps de-risk it so that, we can take a chance and hopefully, it's a great success.
Mm-hmm. And I think this will probably be our last question here. So a question from Warren. So do you think there's an opportunity for a scaled down version of the equipment to be available for use in a home brewing setting?
Hi, Warren. That's why I like you, is that you're always a thinker. You're always thinking of new things. I had never thought about that, but the actual chemical process involved and the engineering that's involved isn't necessarily that difficult. You're taking a nearly saturated gas and you're doing some cleanup processes and you're compressing it and or liquefying it, depending on what kind of pressures you're dealing with. So that's not hard, right? I don't know if a small scale compressor, like say linear compressor, like say in a refrigerator could do it or whatever. I'm sure you or somebody out there in the homebrew world will be the first to do something like that. But yeah, the actual process is not that difficult. The miniaturization, the getting things small enough, even for our scale, and getting things, as I'm sure most people know, like the price has to be right. You can do anything in the world, but it has to work so that, it makes sense financially for people. So yeah, I don't know what those costs are. I don't know what that process is, but it is not a entirely difficult problem to solve. So hey, that'd be amazing. That'd be pretty cool to see.
Thanks, Warren. I'm not sure what you were showing there, but it sounds like Warren has his own prototype going at home. So sounds like a potential collaboration coming up.
I did have my CO2 tank just arrived today for the first time. It was like the stars aligned. So this is very top.
Awesome. Well, thank you so much again, Kirk, for presenting it. And Kirk is actually dialing in from France, so I really appreciate you making the time and making sure everything aligned, because I know it can be tricky as well. So thank you for the presentation, Kirk, and sharing what you're up to with the community here.
Yeah, thanks for having me, David.
Awesome. So moving on then to our second speaker of the day. And so our second speaker is Rohan Nuttall, and he's with Amii and the RLAI group. He's a graduate student there. So he's a student with Matt Taylor, one of the fellows in residence with Amii, and he's working on uncertainty methods for human-in-the-loop deep reinforcement learning. Before this, he worked for a year on sustainability data science applications for the University of British Columbia, where he also earned his bachelor's degree in physics. Rohan, thank you very much for joining us today. And I did want to again give a special thanks and special shout out to Rohan as well. Rohan actually just had COVID and is still feeling some of the lingering effects of that. And so I really appreciate the commitment to the meetup here and making the time for the presentation.
Thanks so much, David. Let me just share screen here. All right, hopefully everyone can see that. Yeah, so today I want to give a little bit of a presentation about how AI can support climate mitigation efforts. So I want to sort of split this talk up into two components. The first one is a case study on forecasting future climate impacts with machine learning. And so this is something, a project that I personally worked on. And then secondly, if there's time, I also just want to highlight some of the applications of reinforcement learning, which, as David mentioned, is the topic of my master's thesis, and climate, because I think there's lots of interesting opportunity there that's sort of come up in the last few years, and I think it's worth just highlighting some of those interesting areas. So I want to start the presentation off by talking about a little bit of a story about this building on one summer's day. So this is the Center for Interactive Research on Sustainability, and it's located at University of British Columbia's Vancouver campus. And I was there a couple of years ago. I was hired by the Sustainability Office to kind of work on data science applications, open data stuff, anything related to trying to improve the university's kind of sustainability outcomes from a data science point of view. And I want to tell you a little bit about sort of what makes this building special and why it's kind of the center of this case study today. So it's what's called a LEED Platinum building. So it's very sustainable. I think LEED Platinum is like the most sustainable that you can be. It's not a net zero building, but it's very close to it. And what's particularly special is it's a passively ventilated building. So passively ventilated buildings, as opposed to traditional buildings, which use HVAC systems to heat and cool according to the weather, passively ventilated buildings are designed, that their architecture is designed in such a way that they can take advantage of the sort of surrounding air currents to cool the building down on hot days, and in the winter months it's very well insulated, so it kind of keeps the heat in. And the other thing about this building, what makes it special, is it's got lots of sensors. So it was kind of considered to be a first of its kind building in North America in terms of the sustainability standards. I think it was opened in 2011. So it was sort of one of the first like really sustainable buildings of this specific kind in Canada. So they equipped it with lots of sensors to measure things like air quality, indoor temperature readings, obviously energy consumption, and a variety of other things relating to the building equipment. And related to one of those variables, indoor temperature. I happened to be sitting in my office, which is on the 3rd floor of the building one day, and I sort of discovered for the first time why passively ventilated could be a bad, maybe not work in all circumstances, because the weekend had just started a heat wave, and heat waves typically mean there's not a huge amount of wind. It's really hot. And I was living the experience of this because I got into the office on Monday and I sat down and I was already sweating within the first 5 minutes just sitting down because it was so hot in the building on the 3rd floor. And this kind of got me thinking, like as climate changes, Vancouver's predicted over the next several decades to feel more like San Diego than its typical kind of northern Pacific Northwest climate. So I was kind of thinking, well, this is an anomaly for sure. This week, I'm sweating at my desk. There's no air conditioning. This passive ventilation is not working too well. But what's this going to be like for the many other passively ventilated buildings that, first, their claim to sustainability is that they don't need air conditioning. But as climate changes, maybe they will need maybe they will need air conditioning, and maybe this type of architecture may not be as optimal in climate change. I'll caveat all this by saying I'm not a building engineer or an architect or designer, so all of my comments on that regard should be taken with a grain of salt. But this did sort of give me this idea to run a research project with some of the sensor data on the building, which I'm going to talk about next. So the idea was to basically say, okay, we've got lots of indoor temperature readings of this building, and we can find the historical weather data as well. So let's pair those two things up and create a data set with which we can use to predict indoor temperature, say at the next hour or the next day, based on the either forecasted temperature or the historical temperature. Then the second thing was we can take these things called the IPCC future climate weather files. So IPCC, as many of you know, is the Intergovernmental Panel on Climate Change. And they run these massive simulations of how the Earth's climate and atmospheric temperature is going to change in accordance with various sort of CO2 concentration pathways. And they have, you can get these statistically downscaled files that are specific to a region like Vancouver. And then you can use that, or the goal was for us to use this data in our model to basically predict what am I going to be feeling in 2050 if I'm still sitting at that desk on the 3rd floor. And so then, the third piece, this is a bit esoteric, but our goal was to kind of estimate the thermal comfort exceedances. And why that's kind of relevant is because a building, obviously, it has to be built to a specific code. So you can't have a building where like 3 months out of the year, it's 30 degrees inside. That just won't meet the public health and safety standards that it was constructed with. So the question is, for some of these passively ventilated buildings, will they actually end up exceeding the kind of building code that they were spec to as the climate shifts? That was kind of these three things were sort of the goal of the case study, which I'll go into a bit further detail into. So just looking at what the data, at least for the weather data, kind of looked like, what you're seeing here, the first two rows are the kind of measured outdoor temperature readings that we were using over the course of the year. These are, I think, 2014 and 2016, and sort of a subsample of, we had about 5 years of data that we were using. And then on the bottom two rows, you can see this is the future climate weather file downsampled data. And it's basically showing you what is the maximum. It's colored according to the maximum temperature on each day in 2050 and in 2080. And this RCP 8.5 thing is the representative concentration pathway, which is what IPCC kind of calls their different scenarios. So 8.5 is like the worst possible scenario. So keep that in mind for the rest of the presentation, because that's the future climate weather file scenario that we were using. And you can see that, you know, the dark red lines show temperature days with a maximum temperature above 30 degrees. So you can see here that, yeah, like by 2080, Vancouver is going to be looking pretty hot in the summer. So we took this data, and this is just a schematic just showing a very simple modeling process that we took. So we took this raw data going left to right, which was hourly kind of weather data, which comprised, you know, solar radiation, temperature, humidity, wind speed, wind direction, basically all the data we could get from the local weather station. And we paired that up with the internal, like the indoor temperature readings from this building. And then we pre-processed it to fit with the modeling, the model that we were using. So we weren't using any kind of like autoregressive or time series model. We chose to use basically logistic regression, essentially. Like we trained up a binary classifier using the model they were using was called NGBoost, which is developed by Stanford. It's called a sort of gradient boosted decision tree, which is particularly good for tabular data. So we pre-processed this data to include essentially lagged features. So because these gradient boosted decision trees don't have the ability to like model backwards in time, you actually have to include these features by basically just adding a couple of columns to your data set to like include like the lagged features. So once we had pre-processed this, we put it into, you know, training and validation to find the best hyperparameters for the model. And then we obviously kept aside a test set and then used that for evaluation on the future climate weather predictions. And the results sort of look like this. Basically, on this plot, the y-axis is showing the number of days exceeding the sort of thermal comfort criteria. And we picked like a thermal comfort criteria from the literature. So like, if anyone's familiar with like building codes, I think it was the ASHRAE MRV something or other. So the details are in the paper here. But you can see that, you know, by the 2050s, there's basically going to be, you know, double the number of days exceeding the comfort standard, which is not great. So it's likely that if the, you know, IPCC, you know, temperature or the future climate weather files from IPCC are correct within that uncertainty bound, like buildings like SIRS are going to probably definitely need to have air conditioning, because no one wants to spend 30 days out of a year in sort of plus, you know, 30 degree conditions. You just can't do any work in that. And by the 2080s, things definitely look more dire. I think one sort of interesting thing about this, obviously it's quite esoteric. We're like trying to predict the number of thermal comfort exceedances in a given year, but we can apply the same methodology to sort of predict, like instead of using indoor temperature as the target, we could use the energy consumption of the building as a target. And so we could so there's lots of interesting things that we could do there, one of which is sort of peak energy demand prediction. That's obviously a massively important, you know, on the energy grid, you have to constantly balance supply and demand of electricity. And for commercial industrial customers, you know, your peak demand of electricity is a huge cost on your electricity bill. So if you can predict reliably sort of when and how exactly that's happening, you can potentially save a lot on your electricity bills. And then potentially, depending on where you're living in the world, you can the grid won't be as burdened and as reliant on, say, like coal peaker plants or natural gas peaker plants. So I think that's one really interesting way to take the work. I think the other takeaway, which was cool here, was that with a building, like you're modeling, like, okay, we're taking it an attribute like temperature, but there are lots of other ways that you can get at this, one of which is using simulations. And that I think in the building energy audit community, simulations are used quite a bit and they're relatively time consuming, and they're not necessarily always calibrated to the building. But what's interesting here is that we didn't use any kind of simulator to get these results. We purely used data from the actual building itself, and we got really well calibrated results, which is great. So it's kind of this interesting thing where you can actually use a machine learning model to get sort of these macro state parameters of something as complicated as like internal building physics, and you don't need any sort of physics solver. So that's kind of like one cool thing. In terms of other like future work, I'll point to this like cool slide. So this is not work that I've done, but what you're seeing here is from a group called Open Climate Fix, and all the little dots are like solar panel energy production output, and it's a satellite image. So they took a similar methodology to what I just presented, but they were predicting solar panel yield as a function of cloud cover. So one challenge with electricity grids and load balancing and so forth is with solar panels, it's really hard to predict how much solar energy is going into the grid at any given time. So potentially a future extension of the work that I presented is, okay, for a given building, we could use satellite imagery to predict like the next hours, weather conditions, and then use that to do the sort of peak load forecasting that I was suggesting. So there's lots of interesting ways that you can integrate new types of data into this sort of simple modeling framework to get cool results. So I'll pause there and kind of transition to the last bit, which is about reinforcement learning and climate. So to give a quick overview here of what reinforcement learning is for folks in the audience who aren't familiar, it's unlike supervised learning. Reinforcement learning, you have this notion of like an agent that at every time step can take an action within an environment where the environment can be something as arbitrary, like it could be a video game, it could be a stock market, it could be a craft brewery, bioreactor, or it could be like a building's HVAC system. And so an agent can take an action to sort of control this environment in some way, and then on the next time step, a reward relating to how good the agent has done on that time step, and like the next state of the environment as a function of the agent's action is emitted to the agent. And so it's this like feedback cycle, very similar to say, control, it's basically a control loop. And the agent learns the best action to take in order to maximize the cumulative sum of rewards. So basically in a stock market example, you could have an agent that's trying to like pick the best buy and sell dates in order to maximize the total profit. And you can cast a ton of problems like this, which is what makes RL so cool. But you can also cast a ton of climate change related problems like this. So this slide is just showing like the number. So there's a paper that was written a couple of years ago called Tackling Climate Change with Machine Learning, which I encourage everyone to take a look at. And it's hosted on the link down at the bottom here. And this is just me filtering for reinforcement learning. And these are all kind of the domains where RL, or where the authors believe RL can have an impact. And so I picked out a couple of the high leverage areas and across these sort of three themes. So in terms of like scheduling, resources, I talked a lot about demand balancing, load balancing on the grid, vehicles like electric vehicles and autonomous vehicles once we have those. So, and each of these kind of links to a paper that I found on the topic too. So there's tons of interesting work. And on the process side of things, maybe Kirk might be interested in the chemical reactions and bioreactor applications as well, or the CO2 capture and reuse. So I just wanted to throw this slide in here just to show the audience how many interesting applications there are. And hopefully maybe the slides can be provided after and you can explore some of these links. But yeah, to conclude, basically from the first case study, a really simple model can predict massive, like big consequences, like say an entire building needing to be retrofitted. And also we can use data to actually learn a model of the system itself. So you don't need a simulator to predict what the future indoor temperature of the building is. You can just use the right data and the right modeling framework. And then Climate Gym, this is a reference to OpenAI's OpenAI Gym, which is like a reinforcement learning kind of open source piece of software. But I think for all of the action or all the applications I mentioned in the previous page, we should have like, the research community should have like similar ones, but for climate themed domains. So like when researchers are trying to prove out new algorithms and the performance of new algorithms, it'd be great if, we could actually also be improving outcomes for certain climate domains, like the ones I mentioned before. And yeah, just a rallying cry to start deploying some of this because time is definitely running out. But yeah, thanks for listening and happy to take any questions.
Awesome. Thanks so much, Rohan. That was really interesting. Definitely, we have a few minutes here for questions as well to wrap things up. So anyone who has a question, again, feel free to use the chat or put up your hand or unmute yourself and chime in. Maybe I'll kick us off again, if you don't mind. I did notice in your first study that you used that RCP 8.5, as you mentioned. Did you also sort of look at, different, I guess, I don't know what you would call it, modeling scenarios from the IPCC?
I think we only looked at RCP 8.5. And I think that may have been like a data availability thing because we were using sort of these downscaled climate weather files, which I believe cost some money. So I think we just decided to obtain the like the worst case scenario. But the framework, you could just swap out the data set if you have it available.
Right. Okay. Makes sense. And then I guess because, yeah, I mean, I was just thinking it would be interesting to compare the different modeling scenarios and potentially what the potentially needed interventions would be, sort of. But yeah, just a thought on that front.
Yeah, I think the really interesting stuff would be, to scale that up to multiple different kinds of buildings, and to probably also have the ability to the future climate weather file stuff is really interesting, and it's cool to see how those things, how a given building is likely to perform under a completely different climate just using data. I think that's really interesting, but there's so much uncertainty with the IPCC files themselves that also kind of needs to be considered. So if you're trying to make a policy decision or you're trying to, as a building operator, make a decision based on this, that's a whole other thing. But I think the interesting thing is if you're trying to make a prediction about what the next week will look like from, say, a peak load forecasting point of view, I think that's really cool and really relevant to the grid and so forth. So I'm really interested in looking further into that area as well.
Absolutely, that makes a lot of sense.
Rohan, I have a question. So have you applied any or thought of any external factors which are not considered? Like, so you used historical data, like wind speed, wind direction, solar radiation, current atmospheric temperature. So as the years goes by, like the temperature is continuously rising. We have more melted, like less glaciers. The wind direction might change. The weather pattern might change. Like more rainy days or drought, more sunny days. So those factors, like how have you thought of like applying those into the predictions and make some corrections, or like how it is like what is your thought on how it will affect the correctness of the predictions? Or when we actually look at 2030, what will be the model prediction versus the actual temperature, or what is the difference we are looking at?
Yeah, that's a great question. Thanks for asking that. So the idea behind using the IPCC future climate weather files is that their modeling process accounts for that. Hopefully, ideally. I mean, the IPCC will look at things like, okay, if in 2030 the temperature is this, then that's going to change the Earth's albedo because, you know, the Greenland ice sheet is going to melt by this much. So I believe that those kinds of factors are reflected in the data that we actually use to train the model. Because the only thing that the model is doing is it's predicting the probability that, you know, this day, given like the previous few days weather, like what is the probability that on this day there's going, like the indoor temperature is going to like result in a thermal exceedance, or like what is the probability that this day will be inside will be like really hot given the weather. And the weather data that we're using comes from a modeling process that I believe accounts for what you were mentioning. But of course, like I haven't looked at all of the factors that IPCC uses in their models, but I'm pretty sure things like glaciers and ocean currents and like changing like, you know, atmospheric currents, I'm pretty sure all of those are modeled for.
Thanks, Rohan.
Yeah.
And Rohan, another question from John in the chat here. What challenges do you see to getting real world applications developed and deployed?
Thanks for the question, John. So yeah, I'm sure David is maybe a better person to answer that question with all of his experience in that domain. But I guess my thoughts, maybe I'll split it into two parts. Like the first part of the question, or the first part will just be about, say, the supervised learning setting and sort of the case study that I presented. And then maybe the second part, I'll try to touch on the challenges with RL, because they're two kind of different things that have different challenges when it comes to real world deployments. So to touch on the first one, I'll also mention that we have not deployed this research. Like that this was a model that we developed, but we didn't deploy it in any meaningful way other than into a publication. So I guess we're cheating a little bit there. I'd love to see it deployed. I think the main challenges are probably bringing the right stakeholders into the group. Like if I think of and making sure they understand what's actually being done, because, you know, in the case of the SIRS building, you know, if we wanted to somehow deploy that model in the building, also like for this specific model, the question is like, okay, how is this actually being deployed? Like is this model like being deployed, you know, from a planning point of view? Is it like, are we just providing these predictions to the building operator and then the building operator gets to do whatever they want to do? That would be a lot easier, like, because then it's just about saying, hey, you can have this model, maybe we have to agree on a price, but the model itself is not doing anything crazy. It's not making any decisions that a human is not involved with. So from a deployment point of view, that's not that hard. We were interested, I mean, and building control is something that we were quite interested in. That's a whole different thing, because if you're getting a computer to try to control a building, then you have to provide a lot more guarantees that computer or that model is going to be correct, so it doesn't mess up the building in some way. And so, but there's definitely guardrails that you can implement around that. So I think it comes down to communication? Like, are you like, what are you actually implementing, and how do you minimize the risks for the customer, especially if they're not too familiar with the ML side of things? So maybe that's all I'll say on the deploying the model case study that I presented. On the RL side of things, it's a bit different because the data requirements are usually quite different, because you need, if you remember back into that like diagram I showed, you have like an action, state, reward, action loop. Whereas, so you kind of need data of that format in order to have an RL algorithm running. And not every enterprise has data in that form. And you run into the same kind of issues where RL typically takes a really long time to train. So you need maybe some kind of simulator, or you need like a good model of the system that you could use as a proxy for the simulator. So that becomes a big challenge on the RL side of things, and just getting the buy-in from the team that you're working with to like grant you access to equipment, or grant you permissions to like actually enable your model to take actions on that equipment. So, but maybe David has some further comments on that.
I'll just say thanks a lot before you let David jump in. That's a really awesome detailed answer. Just so you know where I'm coming from, I'm the DevOps guy at a company that's trying to operationalize in the mobile mining equipment space. So what I'm, if I can paraphrase what I'm hearing from you, is it really is finding a problem that fits the model, and then it depends. You know, you got to deal with the situation that exists there.
Yeah. I mean, again, like I haven't had much experience at all, like actually deploying real world RL, and it's obviously it's a very doable and exciting space, that's for sure. But I mean, I guess in mobile mining, like maybe the challenges are, can you get access to sort of a simulator where you can at least show that, you know, for this equipment, I see you laughing, so access to a simulator is maybe kind of challenging.
They are this space is so far away from the loop that yeah, this is going to make a huge difference in the maintenance of fleets. But yeah.
Sorry, folks, I do have to jump in now. We're just about at time. But John, thanks for that question. And I feel like we'd have lots of follow-up conversation here, because I'd love to hear from your experiences, you know, deploying in the mobile mining sector. And I think there's lots of overlap and parallels between what you're doing and some of these applications as well. Sorry, Raphael, we didn't get the chance to get to your question, but we'll try to answer it offline. I did want to get everybody end the call here on time. So just before we go, thank you again very much to Rohan and Kirk. I really appreciate your presentations, and it's super interesting. I love thinking about this stuff. So really thank you again for presenting today. And then lastly, you know, if you haven't yet, please do sign up for our next meetup on April 26th, and sign up for the newsletter so that you don't miss any of our upcoming programming. And thank you everybody for coming to the presentations today, and have a good rest of your day.